Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today, we are going to discuss about the module Mathematical Preliminaries-I from the paper Electromagnetic Theory. From this module, you may get to know about the following. 1. An overview of the vector algebra and vector analysis, which are very necessary tools in the proper understanding of physics in general and electromagnetic theory in particular, Maxwell's equations in vacuum and the modifications needed in a medium. Then you will also be introduced to a more general definition of position vectors in terms of their properties under rotation. After that, we will find out the relation between the components of a vector in various coordinate systems. Then we will look at the tensor and the matrix notations for representation of the vectors that are introduced. And then we will discuss the concept of vector derivatives and various fundamental theorems of vector analysis which are used liberally throughout the course. Now, we will assume that you are familiar with the elementary definitions of vectors as those physical quantities that have both magnitude and direction and add according to the parallelogram law of addition. Many physical quantities fall under this category. For example, the displacement, the velocity, the momentum, and the force, just to mention a few. We will denote a vector quantity by placing an arrow over it. For example, if we want to denote the vector quantity by the displacement vector r, then we will write the letter r and put an arrow over it. The magnitude of the vector is often written as the modulus of the vector r, or sometimes simply as r. In contrast, scalars are physical quantities which have only magnitude. For example, mass, energy, density, and temperature are some of the examples. Now let us look at the simple definition of vectors. As we know that vectors are those quantities which have both magnitude and direction, and which, if added together, that is, if we take two vectors and if we add them, then the addition of two vectors follow the parallelogram law of addition. And the examples of vector quantities can be taken as displacement, velocity, momentum, and force. There can be many other examples of vectors also. Now let us define the scalar or the dot product of two vectors. So let us take two vector quantities, that is vector A and vector B. Here if you see that when we have an arrow over a letter, for example A has an arrow over it, then this denotes the vector quantity A, and similarly for B. So if we take the scalar or the dot product of two vectors, that is vector A dot vector B, then this scalar or dot product comes out to be equal to the modulus of vector A times the modulus of vector B times cos of theta, where theta is the angle between the vector quantities A and B, and modulus of vector A is the magnitude of the vector A, while modulus of vector B is the magnitude of the vector quantity B. The other important product that we need to define in terms of vector is the vector product, or also called the cross product. So the vector or the cross product of two vector quantities A and B, that is vector A cross vector B, is equal to modulus of vector A times modulus of vector B times sine of theta times unit vector n, where modulus of vector A is the magnitude of the vector A, modulus of vector B is the magnitude of the vector B, and theta is the angle between the vectors A and B, while unit vector n denotes the vector having magnitude unity and direction perpendicular to the plane which contains the vectors A and B. Here it is important to note that the direction of the unit vector n is given by the right hand screw rule, where if the fingers are moved from the direction of vector A to the direction of vector E and curled in such a fashion, then the direction of the thumb gives the direction of the unit normal vector, or the unit vector which is the direction of the vector quantity vector A cross vector B. Another important aspect or property of the vector product or the cross product is that it is anti-commutative, which means that if we take vector A cross vector B, then this is equal to minus of vector B cross vector A. And the reason for this is that when we take the cross product of vector A and vector B, then as I mentioned earlier, that if you use the right hand screw rule, then the fingers are curled from the direction of vector A towards the direction of vector B, and the thumb gives the direction of the resultant vector A cross B. However, if we take the cross product of vector B with vector A, then the fingers are first going to be kept in the direction of vector B, and then they are going to be curled towards the direction of vector A. So using that same right hand thumb screw rule, we see that in this case the direction of the thumb gets inverted, and hence one gets a negative sign. So cross product of vector A and vector B plus cross product of vector B and vector A is equal to 0. Now let us look at the product involving 3 or more vectors. So for the products which involve 3 vectors, there are 2 types of products. One is called the scalar triple product, which is given by the equation vector A dot within brackets vector B cross vector C, and this is equal to if you take a cyclic permutation of these 3 vectors, that is, we can write them as vector B dot within brackets vector C cross vector A, and this turns out to be equal to, again taking the cyclic permutation, vector C dot within brackets vector A cross vector B. So this means that if we take the scalar triple product of 3 vectors, that is vector A, vector B and vector C, then they will come out to be equal to each other provided the 3 vectors are shuffled in a cyclical order. However, if the order is changed, that is from cyclical, if it is made anti-cyclical, then one gets a negative sign. The other important product involving 3 vectors is called the vector triple product, and this is given by vector A cross within brackets vector B cross vector C, and this is equal to vector B times within brackets vector C dot vector A minus vector C times within brackets vector A dot vector B, where the dot product represents the scalar product. And the product involving 4 vectors is given by, if we have 4 vectors, vector A, vector B, vector C and vector D, then if we take the product such that within brackets vector A cross vector B whole cross product with within brackets vector C cross vector D, this is equal to within brackets A dot C vector times within brackets B dot D vector minus within brackets A dot D vector times within brackets vector B dot vector C. Coordinate systems. So now let us discuss the different types of coordinate systems. We first begin our discussion with the Cartesian coordinate system. So if we take the Cartesian coordinates, then a vector quantity A, that is vector A, can be denoted in terms of the 3 components along the 3 axes and the 3 unit vectors along the 3 axes as vector A is equal to A subscript x times unit vector x plus A subscript y times unit vector y plus A subscript z times unit vector z, where the subscript of A denotes the component of A along a particular direction. So for example, A subscript x denotes the component of the vector A along the x direction or the x axis. Similarly, the unit vector x denotes the unit vector along the x axis, the unit vector y denotes the unit vector along the y-axis, and the unit vector z denotes the unit vector along the z-axis. Now, if one has to add two vectors, that is, if we have two vector quantities, vector A and vector B, then the addition of these two quantities is done component-wise. That means that vector A plus vector B will be equal to, within brackets, A subscript x times unit vector x plus A subscript y times unit vector y plus A subscript z times unit vector z, whole bracket close, plus bracket open, B subscript x times unit vector x plus B subscript y times unit vector y plus B subscript z times unit vector z. And when these are added together, then we add the individual components along a particular direction. So the x component of the A vector is added to the x component of the B vector. And we can write these as bracket open, A subscript x plus B subscript x bracket close unit vector x plus bracket open A subscript y plus B subscript y bracket close times unit vector y plus bracket open A subscript z plus B subscript z bracket close whole times unit vector z. Coordinate systems. Now, if we want to write down the scalar and the vector products using these components along the x, y, and z axis, then we first write down these products for the unit vectors. So let us first look at how these products are defined for the unit vectors. So unit vector x dot unit vector x is equal to unit vector y dot unit vector y is equal to unit vector z dot unit vector z, and this turns out to be equal to 1. So if we go back to the definition of the scalar product, we will see that unit vector will have a magnitude 1, and the angle contained between two unit vectors, if they're both along the same direction, will be 0. So unit vector x dot unit vector x is simply modulus of unit vector, which is 1, times cos of theta contained between them, and since theta in this case is 0, therefore cos of 0 gives you 1. Therefore unit vector x dot unit vector x is equal to 1. And similarly for the unit vectors, scalar product of the unit vectors y and the unit vectors z. Now, if we look at the dot product of unit vector x with unit vector y, then this turns out to be equal to the dot product of unit vector x with unit vector z, and this turns out to be equal to the dot product of unit vector y with unit vector z, and this is equal to 0. Again, going back to the definition of the scalar product, we see that the modulus of unit vector x and unit vector y and unit vector z are all 1. However, the angle between unit vector x and unit vector y is 90 degrees, same as the angle between unit vector x and unit vector z, and also the angle between unit vector y and unit vector z, which means that since these three unit vectors are along the direction and orthogonal coordinate system, therefore the angles between the three unit vectors are all 90 degrees, and therefore the cos of 90 degree gives you 0. Hence, the dot product of unit vector x and unit vector y is 0, and this is also equal to the dot product of unit vector x and unit vector z, or the dot product of unit vector y and unit vector z. Now let us come to the cross product of these unit vectors. So the cross product of unit vector x with itself, that is unit vector x cross unit vector x, is equal to cross product of unit vector y with itself, and this is equal to cross product of unit vector z with itself, and this turns out to be equal to 0. Here again, going back to the definition of the vector or the cross product, we see that the magnitude of the unit vectors x, y, and z are all 1. However, the angle between the unit vector x with itself is 0, which is the same as in case of unit vector y and also in case of unit vector z. Therefore, sine of 0 degrees gives 0. Hence, these cross products all give us 0. Now, if we look at the cross product of unit vector x and unit vector y, it turns out to be equal to z. Similarly, the cross product of unit vector y and unit vector z turns out to be equal to x, unit vector x, and the cross or the vector product of unit vector z and unit vector x turns out to be equal to the unit vector y. Here again, if we go back to the definition of the vector product, we use the right hand screw rule, and we see that if we initially have our fingers pointing along the x-axis and then fold them as they move towards the y-axis, then the direction of the thumb gives us the direction of the resultant vector obtained from the cross product of the vector x, unit vector x and unit vector y. So this direction is along the z-axis, and since the magnitude of all the unit vectors is 1, therefore the magnitude of the resultant vector is also 1. Hence, the cross product of unit vector x and unit vector y turns out to be the unit vector z. Similarly, when we take the cross product of unit vector y and unit vector z, then again using the right hand screw rule, one sees that the direction of the resultant unit vector is along the x-axis. Hence, the resultant is the unit vector x. And by similar reasoning, we see that the cross or the vector product of unit vector z and unit vector x turns out to be the unit vector y. However, if we use the anti-cyclical permutation, that is, if we take the cross product of unit vector y and unit vector x, then using the right hand screw rule, we see that the direction of thumb is now inverted. So instead of pointing towards the positive z-axis, the thumb now points towards the negative z-axis, and hence the resultant is the unit vector minus z. Similarly, the cross or the vector product of unit vector z and unit vector y is the unit vector minus x. And by similar reasoning, we get the cross product of the unit vector x and the unit vector z as the unit vector minus y. So using these definitions of the unit vectors and the scalar and the vector products, we can write down the vector product between two vectors a and b as the scalar product between two vectors a and b, that is vector a dot vector b, is equal to a subscript x times b subscript x plus a subscript y times b subscript y plus a subscript z times b subscript z. Here we can see that when we take the dot product, then the modulus of the component of a along the x-axis times the modulus of the component of b along the x-axis is taken, and the unit vector x has a scalar or a dot product with itself, which gives 1. Therefore, the first term comes out to be a subscript x and times b subscript x. Similarly, for the y component of the vector a and vector b, and similarly for the z component of the vector a and vector b. Now, if we take the vector or the cross product of these two vectors, that is the cross product of vector a and vector b, then we can write down this vector or cross product as a determinant with the first row containing the three unit vectors, that is unit vector x, unit vector y and unit vector z. The second row contains the x, y and z components of the vector a, while the third row contains the x, y and z component of the vector b. So in all, the determinant will have 9 components, coordinate systems. Now let us look at the scalar triple product of three vectors, that is vector a, vector b and vector c. So if we take the scalar triple product of these three vectors, then this turns out to be equal to the determinant having 9 elements, where the first row has the x, y and z components of the vector a. The second row has the x, y and z component of the vector b, while the third row has the x, y and z component of the vector c. And the resultant of this determinant gives the value of the scalar triple product of the vectors a dot within brackets b cross c. This result can also be verified from the definition of the vector and the scalar products that we have discussed earlier. In fact, it will be a good exercise if the students try to first evaluate the cross product of vector b and vector c, and then take the dot product of vector a with the resultant cross or vector product of vector b and vector c, and see whether they get the same result as that obtained by solving the determinant mentioned over here. Now, next is the position and the displacement vectors. So if we take a Cartesian coordinate system having the x, y and z axis, and if we take any point P on that Cartesian coordinate system such that the coordinates of that point P are x, y and z, then the position vector r of this point P from the origin of the Cartesian coordinate system is given by the position vector r is equal to x times unit vector x plus y times unit vector y plus z times unit vector z. Now, if we look at the displacement that may happen from the point P to some point P prime, such that the displacement along the x-axis is given by dx, the displacement along the y-axis is given by dy, and the displacement along the z-axis is given by dz when one moves from the point P to the point P prime, then the displacement vector as drawn from the point P and terminating at the point P prime is given by dx times unit vector x plus dy times unit vector y plus dz times unit vector z. Rotations and vectors. Definition of a vector as a quantity having both magnitude and direction are adequate but are not entirely satisfactory. A more satisfactory definition in terms of their properties under rotations better define a vector quantity. So if we consider the coordinates of a point P whose position vector is given by the position vector r and has the position coordinates x, y and z, and the position coordinates x prime, y prime and z prime in two different coordinate systems, which are denoted by the coordinate system having axes x, y and z, and the coordinate system which has axes x prime, y prime and z prime, such that these two coordinate systems differ from each other only in terms of a rotation through an angle theta, but have the same origin. The tensor notation. Now, if we want to express the position vector r in terms of the tensor notations, where the position vector r as defined in the coordinate system having axis x, y and z is given by position vector r is equal to x times unit vector x plus y times unit vector y plus z times unit vector z. Now, if this Cartesian coordinate system is rotated by some angle such that the new axes are x prime, y prime and z prime having unit vectors unit vector x prime, unit vector y prime and unit vector z prime along the x, y and z axis respectively, then the same position vector r of the point P in terms of this new Cartesian coordinate system having axes x prime, y prime and z prime is given as position vector r is equal to x prime times unit vector x prime plus y prime times unit vector y prime plus z prime times unit vector z prime. However, this rotation gives us another representation of this position vector, and we can have many such multiple representations of the position vector depending upon different rotations. So a more convenient and simple way of expressing the position vector in terms of the unit vector is using the tensor notation, where we use the subscripts 1, 2 and 3 instead of the unit vectors x, y and z. And the unit vectors in the tensor notation are denoted by unit vector e subscript 1, unit vector e subscript 2 and unit vector e subscript 3, where unit vector e subscript 1 corresponds to the unit vector x in the coordinate system xyz and corresponds to the unit vector x prime in the coordinate system x prime, y prime, z prime. Similarly, the unit vector e subscript 2 corresponds to the unit vector x in the coordinate system xyz and corresponds to unit vector y prime in the coordinate system x prime, y prime, z prime. And similarly, the unit vector e subscript 3 corresponds to unit vector z in the coordinate system xyz and corresponds to unit vector z prime in the coordinate system x prime, y prime, z prime. So using these new notations, we can write down the position vector as position vector r is equal to x subscript 1 times unit vector e subscript 1 plus x subscript 2 times unit vector e subscript 2 plus x subscript 3 times unit vector e subscript 3, which corresponds to the coordinate system xyz. And similarly, if we want to represent the same position vector r in terms of the coordinate system x prime, y prime, z prime, then this can be written as x prime subscript 1 times unit vector e prime subscript 1 plus x prime subscript 2 times unit vector E prime subscript 2 plus x prime subscript 3 times unit vector E prime subscript 3. And if we want to do a transformation of the position vector from one coordinate system to the other, then that can also be done by taking the dot product of the unit vectors E prime subscript 1, unit vector E prime subscript 2 and unit vector E prime subscript 3, and in such a case the components of the position vector R in the primed coordinate system, they are denoted by x prime I, where I runs from 1 to 3 and denotes the components along the x prime, y prime and z prime direction respectively. So x prime subscript I is equal to summation over j going from 1 to 3 a subscript I subscript j times x subscript j, where a subscript I subscript j are the direction cosines given by the dot product unit vector E prime subscript I dot unit vector E subscript j. That is the dot product between the unit vectors of the two different coordinate systems. And here x subscript j denote the components of the position vector R in the coordinate system x, y, z, that is in the unprimed coordinate system. And j goes from 1 to 3, where 1 denotes the direction along the x-axis, 2 denotes the direction along the y-axis, and 3 denotes the direction along the z-axis. Einstein's summation convention. Now, the number of direction cosines is 9, and not all of these direction cosines are independent. Invariance of the magnitude of a vector implies the following relation. Summation over I going from 1 to 3 a subscript I subscript j times a subscript I subscript k is equal to delta function subscript j subscript k, where the delta function delta subscript I subscript j is the Kronecker delta. Since Kronecker delta is symmetric in two indices, this implies that 6 relations and 3 of these 6 relations are having independent coefficients. Now, Einstein's summation convention leads to further simplification. An index or a subscript can appear only once or twice. Each index will take the values 1, 2 or 3. Then, an index that appears once is a free index, and every free index represents a set of 3 equations. An index that appears twice is a dummy index. The index is understood to be summed over. Finally, one dummy index can be freely replaced by another. Matrix representation. Thus, if we now take the product of the quantity or the number a subscript I with itself and do the summation for I going from 1 to 3, that is summation over I going from 1 to 3 a subscript I times a subscript I, then this is equivalent to a subscript I times a subscript I, and this can again be written as equivalent to a subscript j times a subscript j, and this turns out to be equal to a1 square plus a subscript 2 square plus a subscript 3 square. That means that when we run the summation of I going from 1 to 3 over a subscript I times a subscript I, it gives us the final value as a subscript 1 square plus a subscript 2 square plus a subscript 3 square. Again, now let us look at another property where we are wanting to define the primed coordinate in terms of the unprimed coordinate. So the free indices on both the sides must match in the equation and on each term of an expression. So the expressions then can be written as x prime subscript I is equal to a subscript I subscript j times x subscript j. So similarly, if we write x subscript I times x subscript I, then this can be written as equal to x prime subscript I times x prime subscript I, and this is because if we write x subscript I times x subscript I, then we can write this as equal to a subscript I subscript j times a subscript I subscript k times x prime subscript j times x prime subscript k, where a subscript I subscript j times a subscript I subscript k is the Kronecker delta subscript j k, which means that if the subscripts j and k are equal, then the product a subscript I subscript j times a subscript I subscript k will return 1, and if the subscripts j and subscript k are not equal, then this product will return a value 0. Now let us look at the matrix representation. So matrix representation is often very convenient when we want to write down the coordinates and the components. So in case of matrix representation, the components of the coordinates along the three axes can be represented as a column matrix. So xi can be written as a column matrix having components x subscript 1, x subscript 2 and x subscript 3, while the quantity aij, where a subscript I subscript j, both subscripts I and subscript j run from 1 to 3, can be written as a matrix containing 9 elements, where the first row has elements a subscript 1 subscript 1, a subscript 1 subscript 2 and a subscript 1 subscript 3. The second row has 3 elements, that is a subscript 2 subscript 1, a subscript 2 subscript 2 and a subscript 2 subscript 3, while the third row has the 3 elements a subscript 3 subscript 1, a subscript 3 subscript 2 and a subscript 3 subscript 3. Now using these notations of representing the coordinates and the diagonal and the coefficients which are denoted by the diagonal matrix, we can then write down the equations of the primed coordinate system as x prime is equal to a times x and x transpose times x is equal to x prime transpose times x prime, while the coefficients which are written as the diagonal matrix can be represented as A transpose times A is equal to the identity matrix I. Differential operators. Now, if we look at the equation concerning the coefficients, that is the transpose of A times A is the unit matrix, then from this it implies that the transpose of A is equal to A inverse. And from this equation one can conclude that the coefficient A is orthogonal. Now, by using these definitions of the coefficients and the transformation that we defined earlier of the primed coordinate in terms of the unprimed coordinate, we can now define the inverse transformation which defines the unprimed coordinate in terms of the primed coordinate and the coefficient. So the unprimed coordinate x can be written as A transpose times x prime, where x prime denotes the primed coordinates. Now next, what we want to define over here are the vector differential operators. We know that physics deals with quantities that are scalar, vector and tensor fields. So an example of the scalar field is the charge density. Similarly, an example of the vector fields can be taken as the electric field or the magnetic field, while the example of a tensor field can be taken as the Maxwell energy stress tensor. Now, when we talk of these fields, then it is important that we define the differential operators that act on these fields. So we define 3 different types of operations that involve the differential operator del. First is the gradient operator. So the gradient operator or the del operator is given by del x unit vector x, then del y unit vector y, and del z unit vector z, where del x is the x component of the gradient, del y is the y component of the gradient, and del z is the z component of the gradient. In terms of the tensors, we can then just write the del operator as del operator is del x subscript I is equal to del x subscript I times the unit vector x subscript I. Now, if we have a scalar field given by phi as a function of vector x, that is phi as a function of x, y and z, then the gradient of this scalar field, that is del operator acting on the scalar field phi, is given as del phi by del x, del phi by del y, and del phi by del z. So del phi by del x, del phi by del y, and del phi by del z are the three components of this gradient acting on the scalar field. The divergence of a vector field is defined as divergence of the vector field E as a function of vector x, that is the scalar product of the del operator or the gradient operator with the vector field E as a function of the vector x, and this is equivalent to del E subscript x by del x plus del E subscript y by del y plus del E subscript z by del z. And this can also be written in terms of the tensorial notation as del E subscript I by del x subscript I, where the subscript I runs from 1 to 3 and denotes the summation over the subscript I. Differential operators. Now, the next operation using differential operators that we define on the fields is the curl operation of a vector. So the curl of a vector E as a function of vector x is defined as the vector or the cross product of the del operator with the vector field E as a function of vector x. And this turns out to be equal to bracket open del by del y E subscript z minus del by del z acting on E subscript y bracket close unit vector x plus del by del z acting on E subscript x minus del by del x acting on E subscript z bracket close unit times unit vector y plus del by del x acting on E subscript y minus del by del y acting on E subscript x bracket close times unit vector z. In tensor notation, the curl of a vector field can be written as del vector cross E vector whole subscript I is equal to epsilon subscript I subscript j times del by del x subscript j acting on E subscript k. And another important operation which is denoted as the Laplacian operator, where the Laplacian operator is the scalar or the dot product of the del operator with itself. So del operator dot del operator is equal to del square, which is called the Laplacian operator, and this turns out to be equal to del 2 by del x square plus del 2 by del y square plus del 2 by del z square is equal to del 2 by del x subscript I times del x subscript I. Here it is important to note that the del operator is both a vector as well as an operator. And from this property of the del operator, one can see that the vector or the cross product of the del operator with itself gives 0, and therefore the scalar triple product of the del operator with a vector quantity A, that is del operator dot within brackets del operator cross vector A is equal to, if we do a cyclical rotation, del operator cross del operator whole within brackets dot vector A. And since the del operator cross del operator gives 0, therefore the resultant turns out to be 0 for this equation. Integrals involving vectors. Now let us discuss some more vector operator identities. So if we take the vector triple product involving del operators acting on the vector A, that is del operator cross within brackets del operator cross vector A, then this turns out to be equal to del operator times within brackets del operator dot vector A bracket close minus the Laplacian operator acting on the vector A, that is del square vector A. Another important property involving the del operator and a scalar field and a vector field, where the scalar field is defined by phi and the vector field is defined by vector A, is given as del operator dot or the scalar product within brackets the scalar field phi times the vector field A is given as bracket open vector A dot del operator bracket close whole times phi plus phi whole times bracket open del operator dot vector A bracket close. So this relation basically denotes the scalar product of the del operator with the product of a scalar and a vector field. And now let us define the identity which involves the vector or the cross product of the del operator with the product of the scalar and vector field. That is, where the scalar field is denoted by phi and the vector field is denoted by the vector A. So del operator cross bracket open phi times vector A bracket close is equal to phi times bracket open del operator cross vector A bracket close minus bracket open vector A cross del operator bracket close whole times phi. Now let us look at some of the identities which involve integrals and vectors. So let us denote the line integral of a vector. So integral with limits a to b vector f as a function of vector x dot dl vector, where the limits of the integration are going from a to b over some specific path, and dl vector denotes the length element on this path. And if the path is closed, then the above integral can be represented as the integral over the closed path vector f dot dl vector. Similarly, one can define the surface integral over a surface S as the for a vector field f as a function of vector x as surface integral over vector f as a function of vector x dot vector dA, where the vector dA is the surface area vector, and this surface integral is defined over some specified open surface. In case the surface is closed, then we represent it by closed surface integral on vector f dot dA vector. And similarly, we can then define the volume integral as volume integral over some volume V, phi as a function of vector x d cube x, where phi is some scalar field and d cube x denotes the volume element of this volume V. The fundamental theorems. Now let us discuss some of the fundamental theorems which we will be using throughout our discussion of the electrodynamics. So the first of these fundamental theorems is the Gauss's theorem, or also called as the Gauss's divergence theorem. So if we have any vector function A, then the volume integral of the divergence of the vector function A over the volume element d cube x is equal to the closed surface integral over the vector function A dot unit vector n times dA, where dA is the surface area element of this closed surface S, and the unit vector n is the unit normal vector on this closed surface S, having its direction normal to the surface under consideration. The second of these fundamental theorems is the Green's first identity. So if we have two scalar functions given by phi and psi, then the volume integral over the volume element d cube x of the function bracket open phi times Laplacian operator acting on psi plus gradient of phi dot gradient of psi bracket close is equal to the closed or the bounded surface integral S over the surface area element dA acting on or evaluated on the scalar function phi times bracket open unit vector n dot del operator bracket close times the scalar function psi, where the unit vector n is the unit normal of the surface area element dA and the del operator is the gradient or the operator as defined earlier. And the third important theorem that we will be utilizing throughout our discussion of electrodynamics is the Stokes theorem. So if we have any given vector function vector A, then the closed or the bounded surface integral over S of the curl of the vector function A whole dot unit normal n integrated over the surface element dA is equal to the closed contour integral C or the closed line integral C of the vector function A dot dl vector. Here S is an open surface and C is the contour around it, and the vector dl is a line element along it. So students, now let us summarize what we have learned in this module. The essential mathematical preliminaries of the vectors were discussed. Then after having done that discussion, we gave the usual definition of vectors and Then a more basic definition is provided which brings out the relation with rotations in terms of vectors. Then the entire vector relations is discussed in terms of the tensor notation, and the usefulness of these tensor notations is also brought out. Then the differential vector operators are introduced. Some of the fundamental theorems like the Gauss's theorem and the Stokes theorem, which are crucial in electrodynamics, are written out. Thank you.